Hi everyone, thank you so much for joining the video. Today we're going to be learning about entropy. So the first learning objective is to explain that entropy is a measure of the dispersal of energy in a system, which is greater the more disordered a system. And then we're going to explain the difference in magnitude of the entropy of a system of solids, liquids and gases, and for a reaction in which there is a change in the number of gaseous molecules. And then we're going to calculate the entropy change of a system and related quantities for a reaction given the entropies of the reactants and products. So now we're going to introduce the idea of entropy. And the basic idea is that entropy is equal to how much disorder there is in a system, in a substance. So the more disordered something is, the greater the entropy it has. And therefore, gases have the highest entropy because it's got a million particles moving rapidly and randomly in many different directions. Whereas in solids, the particles are all fixed in, all the particles are in a fixed position, vibrating, and so they have the least entropy. And by the second law of thermodynamics, this states that the entropy will naturally increase over time. And also, entropy is denoted by the letter S, and it's measured in joules per mole per Kelvin. Now we're going to see how to calculate entropy changes, and we use this formula. So delta S stands for change in entropy, and it's equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. And so from this, we can see that in reactions when there is an increase in entropy, the delta S is positive because the reactants will have less entropy than the products. And in reactions where there is a decrease in entropy, then the enthalpy change will be negative, so it will be the opposite. And in keeping with the second law of thermodynamics, reactions in which there is an increase in entropy, those ones are favourable because the second law states that the entropy increases over time. And so we're going to look at this example, calculate the entropy change for this reaction. And so what we do is we use this formula. So we have delta S, and first we need the sum of the entropy of the products. And so these are these ones here. And the thing to remember with these entropy changes questions is that you have to multiply by how many moles there are of everything. And so first we have to have 2 moles times by the entropy of the carbon dioxide. And so we have 2 times 214. And then we have to add that with 3 moles of the water. So that's 3 times 70. And then we minus the sum of the reactants, so the stuff on the other side. So we have 1 mole of C2H5OH, which is minus 161. And then you can use a bracket, so you're minusing all of the sum of the entropy of the reactants. And then you add on 3 of this 205. And then you just plug in all the numbers, and this comes out to be minus 138 joules per mole per Kelvin. And you need to remember the units of this entropy. However, they have given it in this question for us. And so from this, we can say that this reaction is not favourable as there's a decrease in entropy. And the way in which we can make it more favourable is by adding heat. So by raising the temperature, that will increase the entropy. Because by increasing the temperature, we'll increase the number of particles with the activation energy. And so more products will be formed. So that means that this sum of entropy of the products will be much bigger. And so this delta S should hopefully be positive. Now we're going to look at some questions. So for number 1, predict whether there will be a change in entropy for the following reactions. For A, sodium chloride solid to sodium chloride aqueous. And we know that entropy increases when you go from solid to gas. And that's because the particles move about more, so there's more disorder. And so if we're going from 1 mole of a solid to 2 moles of aqueous ions, 2 moles because we've got 1 mole of Na plus aqueous ions and 1 mole of Cl minus aqueous ions, that means that the entropy will be increasing because we've turned them into liquids, and also the disorder has increased. And so delta G, and so delta S, so the change in entropy, will increase. And then for B, we have 4 moles of gas on the left, and this goes to form 2 moles of gas on the right. And this is quite easy to work out because they're both gases. So if we're going from more moles of gas to less moles of gas, then that means that the entropy is decreasing because we've got less gas, so we've got less disorder. And so delta S decrease. And then for C, we've got 2 moles of gas on the left, and also 2 moles of gas on the right. And that means that there'll be very, very little change in entropy because we've got the same number of moles of gas on each side. And so delta S remains nearly the same. And then finally for D, we've got we've got a Ba plus and 2 NO3 minuses. So we've got 3 moles of aqueous ions for the Ba NO3 2. And then for the K2SO4, we've got 2 K pluses and 1 SO40 minus, so that's another 3. So we've got 6 moles of aqueous ions on the left. And on the other side, we've got 1 solid, and then we've got a K plus aqueous ion and an NO3 aqueous ion, but we've got 2 of these, so that means we've got 4. And so we form 4 moles of aqueous ions and 1 solid. So that means that the entropy will decrease because we're forming a solid, and the entropy of the solid is much less than for aqueous ions. And so delta S will decrease.